Okay, so what's going to happen is this. Okay, so y'all are used to like hopefully, if I give you like an initial condition and I ask you to estimate f of 0.2. You would write the equation of the tangent line. Obviously, you need more information about the derivative, which you're used to from slope fields and stuff now, okay? But say that this is my function, okay? And f of 0 is 4. If you write the equation of the tangent line, I can actually fill 0.2 into the tangent line, and it gives me a fabulous approximation of what the answer actually is. Do y'all remember that? Okay, locally linear. Like the tangent line locks on, and if I zoom in, they almost merge together for a little while and then they separate. Depending on how fast it's increasing and decreasing, you don't want to go too far to approximate it. Like I have no business going, now approximate f of 4. I mean, do I have any business approximating f of 4 way out there with that tangent line? That's a really bad idea. I guess unless you knew enough about the function. If it was increasing slowly, and you had f of 2, and you wanted to use it to do f of 4, it still wouldn't be that great, but it wouldn't be that bad. But that's only in the case if it's increasing slowly or decreasing slowly, in which case, that's not even what we're talking about, because you just know you're going to be handed lots of functions. Okay? Alright, so we all agree that's a really bad idea. However, people do it. Let me go out to f of 2, or it doesn't matter, f of anywhere else. So you're going to be surprised that now all of a sudden you're going to be given like f of 0 is a number, and you're going to be asked to approximate f of 3. And you go, I should not be doing that, okay? You're used to f of 3, and I'll approximate f of 3.1 with your tangent line. Euler, his name is actually spelled this way. He's a mathematician that came up with 2.718, okay? Famous mathematician. Euler came up with Euler's method that a lot of times people use. And by the way, as you stop and think about who would even do this stuff, many times people don't have equations. They're looking at their data. And they need to approximate something. Maybe they're doing projections into the future to see where their sales are going. Maybe they're trying to see medical trials or whatever. A lot of times they're only looking at data, and they've got to do some approximating to figure out some things. Anyway, what it does is it actually, let me do this picture because I can do it better. I can't draw that one very well. But if I wrote the equation of the tangent line here, and I want to know what's going on up here, that's a really bad idea. They're very far apart. But what Euler did was he said, okay, let's write the equation of the tangent line and say this is 1 and this is 3, okay? If I take a step of, if I go make my dx equal to, my change in x just equal to 0.2, then my next one is 1.2. So when I get on my number line, at 1.2, he didn't fill it into the purple. He filled it into the tangent line, because at 1.2, that's pretty good, isn't it? Mm-hmm. You're not quite on the purple, but you're really close. So he said, let's just don't go very far. And so he actually fills 1.2 into the tangent line, so he's not really quite on the curve. And he writes the equation of another tangent line. Then he gets on down the road, blah, blah, blah. The next one would be 1.4. So he fills 1.4 now into the yellow line and writes the equation of a tangent line. Then he fills in 1.6 to the tangent line and writes the equation of another tangent line. And again, I'm not drawing it very well, but this is what happens. Let me draw it better. I've got it too close together. Okay? So you write the equation of a tangent line. You're filling a number later on. This is real blown up, okay? You're filling a number into the tangent line and writing an equation of your next tangent line. Then you're filling a number into the tangent line, and you're writing an equation of another tangent line. Then you're moving along, and can you see it starting to follow your graph at least? So your estimation by the time you get there is still not too far off. It's a decent approximation. We do it much like Riemann sums with relatively large increments so we can teach you how to do it. But if you're really gonna write a computer program to do a lot of them, y'all see if I made those increments smaller, I'd be following that. I'd be building scaffolding right along that curve if the increments were smaller. Does that make sense?
Yeah.
Pretty brilliant. So you're just moving along, writing equations of the tangent line, but the deal is you're using a y value that's itself an estimation over and over again. Okay, so let me show you one. I think I have one here. Okay, I'll just read one now.
Is this a new topic?
New topic, Euler's method, okay? All right, so this is consider the differential equation dy over dx. You'll be given is x minus 1. Let y equals f of x be the particular solution. Some of y'all haven't lately been finding the particular solution means solve all the way through y given the point that you're given. Like you want what was the original equation, not with the plus c, you want everything filled in. The particular solution to a differential equation, this is a differential equation, with the initial condition of f of 0 equals 2. And it says use Euler's method starting at x equals 0 with 2 steps. You'll see all these words on the worksheet I give you. Starting at x equals 0 with 2 steps. Okay? Of equal size, that's important, to approximate f of 0.6. Which normally I'd be like, what are you doing? Like, don't go from 0 all the way to 0.6. You might want to go from 0 to 0.1, but you don't want to go from 0 to 0.6. Ironically, with Euler's method, it might take a while, but you could go from 0 to 6 and get a great approximation with tiny increments that are just following it as you go. Let's see, and then, okay, so here we go. So that's the wording that you would see. I'm sorry, I didn't pull it into my slides. So say, given the differential equation, find the particular solution of a graph that, f of 0 equals 2, start at x equals 0 with 2 steps of equal size to approximate f of 0.6. So now I'm going to erase this. And if I'm doing 2 steps of equal size, I'm going to go to 0.3. So I'm taking those and dividing it by 2. I'm going from 0 to 0.6, dividing it into 2 parts. Like a Riemann sum at first. Okay? So do you see my 2 steps? This will be my first step. And this will be my second step.
Why do you choose 0.2?
I should not have done that. I didn't even know I wrote down a 2. What should I write down?
3.
A 3. Yeah. Thank you, Emma. That would be horrible to start off easy with something confusing, okay? You might not want to write down what I do next because this is how I actually learned it and started teaching it, and I want to do it so that you see the sense behind it, but I'm going to give you a chart that'll work every time, to be honest with you, okay? I kind of battled not using the chart for a while, but my students love it in AP workshops. I see it now, so anyway, I'm going to show you what you're doing, and then I'll show you the chart. And I'm guessing most of y'all will use the chart. And it's great for the AP Reader. By the way, I'm going back this year. So I'll be grading whatever exam y'all are taking. I won't be grading yours, but.
You should grade ours.
Yeah, you should. Give us your lines.
Give extra points.
So anyway, we like seeing the chart. Like, it's good. Okay, so it's fine if you do the chart on your free. This is a free response problem, by the way. All right, so you're going to write the equation of a tangent line when you're doing Euler's method. Euler's method is this is all it is, girls. It's linearization on steroids, okay? It's just going to do it over and over again. So step 1. All right, I'm going to use this point on step 1. So I'm going to say y minus y equals m times x minus x. Do y'all see that? Okay, and again, you don't have to write it down if you just watch, but you can write it down or review it later. Where am I going to get y minus y equals m? Where am I going to get my slope?
Aren't you the CY tangent?
Huh?
I was gonna say, like, don't you have to, like, separate the variables and, like, just find dy minus dx? Or, wait, never mind, just
Well,
find
they
dx.
demanded I use Euler's method to approximate. So that means you're starting to write equations of tangent lines. They didn't ask you to find the particular solution. Do you see what I mean?
Yeah, so you can just plug in.
By the way, it's a great question that Grace just asked. There's a lot of these dy over dx's that she and I, we could separate our variables all day long and we couldn't integrate it. And so we would be dependent on Euler's method to get an estimation. Some things we pull apart and we don't know the antiderivative of, and then we're stuck, okay? But that doesn't mean we can't get a great estimation. Don't forget that about Riemann sums also. Ironically, Grace, we're gonna do that on the B part, okay? All right, so anyway, I gave it away. Did y'all see where I'm gonna get my slope?
Yeah.
All right, so dy over dx is the slope of whatever this is. And so if I fill in, you might sometimes have to fill in x and y like you do with your slope fields. It all's married together. But right now I just need my x. So this is my first step, -1. Okay, my second step, I'm gonna go to this one. So I'm gonna say y minus y equals m times x minus x. But I have a problem. I can find the slope. How can I find the slope of that new line? I'm gonna say 0.3 minus 1, 0.3 minus 1, and I get negative 0.7. I know I should write negative 0.7, my friends. How am I gonna find y? I can't fill it into the original, so I fill it into the tangent line before it. Remember, we're trying to follow a below or beneath it or up and around it. And so I actually am going to fill 0.3 into this tangent line. Do y'all remember? I don't know what the graph looks like, but remember what I'm saying. You write the equation of a tangent line, and then you move over a little bit, and you fill the number into the tangent line and write another tangent line to help yourself follow the graph. Okay? So if I fill 0.3 into the tangent line, I'm going to have y minus 2 equals -1 times 0.3 minus 0. And I wouldn't do that in my head, but the reason I did it in a different color is, do you see, to get this, I needed to go back to that, okay? So, that's gonna be -0.3, and then I'm gonna add 2 to it. I believe I get 2.3, I don't remember that number. What have I done wrong?
No, it's not, because you -0.3 plus 2.
I should get 1.7, what am I doing
You
wrong?
do.
Oh, it's a -0.3 plus 2. So I get 1.7. I knew I didn't remember that number. Okay, remember it said 2 steps? So now you've just written your second step. And so guess where you're gonna find f of 0.6 from?
0.6 into that.
You're gonna fill it into your second tangent line that you've written. You're gonna fill 0.6 into the second tangent line, and you're done, okay? So I'm gonna say y is equal to 1.7 plus -0.7. X is 0.6 minus 0.3. So I get 1.7 plus, this is gonna give me -0.21, which I think is 1.49.
Yeah.
Is that right?
Mm-hmm.
Then what you would say is, you would say, so f of 0.6 is approximately equal to 1.49. So I wrote the equation of tangent line with the point they gave me using the slope they gave me. So y'all listen to that? Then to get the next point, I can't fill the x into the original, so I fill it into that tangent line that's following the original to get my new y value. So it's called an iteration, if you've ever heard that word. You're just building as you go, okay? Now, it's very similar to linearization. If I'd have just stopped here and filled in a number into my equation of my first tangent line, it would be an approximation, and many times then they say what Grace said, find the original and see how far off you are. All right, so before I do the B part, let me show you the trick, all right? So here's a chart you will probably use. In fact, since this is being recorded, if you want to watch it later, I'm going to erase all this, but you won't lose it all. It'll be the first part of this presentation. All right, so that's why it works. I tell you what, and everything in me is like, before I show you the chart, remember what you're doing, Okay, you're writing the equation of a tangent line. Okay, well, that was supposed to be a tangent line, but anyway, at a point. You fill the next point into the tangent line instead of the original and write another tangent line. You fill the next point into that tangent line and write another tangent line. And so by the time you get way out here, your approximation is not very far off, like it would have been if you'd only written one tangent line. Do y'all see what I mean? The smaller increments are better. But a lot of times they don't make you do small increments, they just wanna see if you know how to do it. Remember with our Riemann sums, isn't it the more rectangles the better? But they only make you do like 4 instead of 4,000, okay?
Would they ask you like how they do with Riemann sums if it's like an over approximation or an under?
Yeah, that's gonna come up, thanks. Oh yeah, cause you're thinking of the, probably it came up in, the free response number 3, that's an under or over. Sometimes you can't answer that, but since that one was increasing, the left's gonna always be an under. This one, because it's concave down, then all my tangent lines are always gonna be an over approximation. So that's a great question. Linearization or Euler's method, y'all see what Emma's asking? If they say is this an under or over with linearization or Euler's method, which are kind of the same thing. If it's concave up, everything your scaffolding is gonna be under. And all you gotta say is concave up. You would need to know the second derivative for that. Okay, so I've explained what we're doing. Here's the chart. You start off with a point. Next to it, put your other given, dy over dx. Because the chart's not helpful if you forget. You'll get your categories mixed up if you don't understand all what you're doing, okay? So do you see you'll be given a point and slope, so write those down on your chart. And then, put those papers on. Alright, so anyway, you'll be given a point and a slope. And then the next thing you do is you're gonna find, you're gonna write down your dx, you're gonna find dy, and then you're gonna find your new point, x plus dx, x plus dy. So what's happening is, your scaffolding, when you move over, you move to a y plus dy. Thank you. Do y'all see every time I move over on my scaffolding, when I plug it in, I get a new x and a new y that I use to write another one, and I keep getting a new x and a new y. Alright, so you'll be given dy over dx, you'll have to be given an initial point. Dx will be your steps, so it'll be the same thing every time. This column should not change. In the example I just did, they said start at f of 0 and use it to approximate f of 0.6 with 2 equal steps. So I'm going 0.6 units divided by 2, so each delta x is 0.3. We're only going to do 2 steps. I started with the 0.01, didn't I?
0, 2.
Thank you. Wow, that would have messed me up. So I started with the 0.02. And the dy over d, it's up here, is x minus 1. So let's just fill them in as we go. Let's just let it flow. But dy over dx is given. You might have to fill in x and y like a slope fill, but right now I just need x. So this is -1. And then notice if you multiply those 2 columns, what do you get? Dy, don't you? So then you'll multiply these 2 columns and you get -0.3. And so now you know what your new point is.
Yeah.
You have x plus delta x, so you have x plus delta x, so you have 0.3. And then you have y plus delta y, so you have 1.7, which you might recognize those numbers. So that's your new point. You pull it down here to write the next step. Now you're starting on your next tangent line. As if, my big fear is you're gonna forget what you're doing, but just look at the dotted line. Alright, so now I'm gonna find the slope based on this. Dy over dx gives me -0.7. the step every time, dx, you're changing your dx by a set amount, kind of like a Riemann sum. And then how are you gonna get dy? Multiply and you get negative 0.21. And then x plus delta x plus dx is 0.6. And y plus delta y is 1.49. And so then you would say f of 0.6, use the approximation, is 1.49, and they do accept the chart. Okay, now let's see how we did. It's back to what Grace was asking. Grace, we had dy, the b part, and by the way, to Celine's question, this would only be on BC. AB doesn't do Euler's method, but some things that we do, they do. So, you know, second semester is almost always exclusive. Almost all the topics are BC, but not all of them. All right, I'm going to separate my variables. dy equals x minus 1 dx, and that's good and separated. So I'm going to integrate, and I get y is equal to x squared over 2 minus x plus c. You only need 1 plus c. Somebody wrote 2 of them on there, but plus c just takes care of the whole constant. Now I have initial condition, in which case I recommend you fill it in right here before you do anything else. My initial condition was 0, 2, right? Is that right? So I get 2 is equal to c. So my equation is y equals x squared over 2 minus x plus 2. I don't have the calculator pulled up, but I have it on the sheet. And we got f of 0.6. I filled it into the, now I actually know what the equation was. F of 0.6 is actually, when you fill that into the original, 1.58. So what was our error in measurement? Because we approximated 0.6 to be approximately 1.49. So our error, we were only off by an absolute value of 0.09, right? So it's just really a small error in measurement compared to the numbers that we're getting, okay? So we were close. If I use smaller increments, instead if I was 1.1 from 0 to 0.6, I'd have a tons better approximation. Does that make sense too? Good news is you only have to do a few. The chart, you kind of don't care how many you do. I mean, you can just fill it in like crazy. So, I think I have another one. Okay. Suppose a continuous function, its derivative f prime, have values that are given in the following table. They'll give you a table. And this is real important. F of 2 is 5. Use Euler's method. I'm sorry, I'm saying his name right. Euler's method with 2 steps of equal size of 0.5 to approximate f of 3. So I'm going to go to f of 2, f of 2.5, and f of 3. And I would write the equations of the tangent lines, but you probably like the chart, so let's do that. So we'll do our chart. All right, it goes x, y. Then you put your given dy over dx. They'll give it to you some way. Dx is set in stone, 0.5, 0.5, only 2 steps. If there were more, write it down. The next one, you multiply and get dy, and then you end with x plus dx, y plus dy. You probably already kind of learned it, I hope. All right, so what's my initial point? 2, 5. Okay, and dy over dx at 2. Yes, isn't this the slope at 2, 5?
Yeah.
All right, so it's 0.4. You multiply these two, and does that give you 0.02? 0.02?
No, because you just point
Oh,
to
0.2, because I would have 20. Okay.
Yeah.
So 0.2, so you have 0.2. All right, x plus delta x, this is x plus delta x is 2.5, and y plus delta y is 5.2. All right, so you bring that down here, 2.5, 5.2. All right, now you know the slope at 2.5. You can fill in, they usually want you to fill in the chart too. So our new y value is 5.2. The slope is 0.6. Multiply these, I believe you get 0.3. And so I have 2.5 and 0.5 is 3. And 5.2 times 0.3 is that?
Plus.
I'm sorry, it's plus, it's 5.5. So add your delta x, add your delta y, and you're through. So f of 3 is 5.5. That's your estimation. Now look at what you never needed. You never needed that. That throws some kids for a loop. They're just like, I never use that. It's just sitting there to make the chart look complete and to really test you and see if you know what you're doing. If they give you a chart, chances are you're not going to need all of it. Just use the parts you need and don't let it worry you. Okay? Some students would even try to go further thinking they have to use that one, but you would need that one for the next scaffolding part. Okay, so, you know, I don't know if you want holes punched in your worksheets or not. I accidentally did it. So take 2. You've got your 2. Alright, so Caitlin, take 2 and pass it. And Grace, take 2 and pass it. And they have holes in it. Do y'all want holes in it from now on? I don't know how to do that.
Medical care is gonna be
Okay, this is your homework, so I'm not gonna do it, but the good thing is you got your answers. And let me check, I think all the answers are right on this. I think, I'm not sure. I don't have any corrections on it. Look at the back window. Please look at this table on the back, real quickly. The table on the back. You're gonna have more information than you need, okay? So read the problem. You're going from -2 with a step size of 1.5, okay? So like on mine where I worked it out, I don't need all those values. I actually drew from -2, I did a step of 1.5, so I drew an arrow to the next one I needed, and then 1.5 more to the next one I needed. Do y'all see what I mean? You're only gonna need, if you wanna circle it now, you're gonna need -2, and the next one you need if you're taking a step of 1.5 is -0.5, and then take another step of 1.5 will take you to 1. Do y'all see what I mean? So those are only ones you need. And I'm guessing you're gonna use the taking, okay? Just reach out to me if you have trouble. All right, now, the last thing that so Euler's method is super easy, especially with the chart. Hoping you understand what you're doing. Okay, now, I wanna show you something else. And we'll just keep reviewing, but this is something else new, okay? I'm going to show you today how to take derivatives of inverse trig functions in 7 minutes or less, okay? I could derive it, okay? If I switch x and y, I get x is equal to sine y. Which actually, did y'all see how I switched x and y to get the inverse? And this totally shows you what we did in pre-cal. If I solve for y, I have y is the inverse sine of x. Did y'all see if I solve that for y?
Yeah.
All right, so once again, inverse sine is finding an angle. You already have the ratio. There's a lot of domain issues with arc sine, arc tangent, arc cosine, okay? I'm gonna worry about those another day. I'm just gonna show you a formula that I think all of you will and should memorize, but I'm gonna derive it and then I'll show you the formulas and you can have some time to get used to them. Right now, you're just gonna be plugging into a formula. I'm gonna draw a picture of what's happening here. My angle here is y. Is everybody okay with that once I'm on my inverse?
Yes.
Because that's what this means. So anyway, here's my angle y. And I get a ratio of x over 1. We'll be drawing a lot of triangles this semester. The missing side is the square root of 1 minus x squared. Let me pause. Is everybody okay with that scenario? Okay? Alright, so now I'm going to take the derivative using implicit. Kind of like with inverse functions that I didn't put on the last test. The derivative of this is 1. The derivative of sine is cosine. But then you always go back and take the derivative of y, so that's times y prime. So I get y prime is 1 over cosine y. Okay? Which would be easy to remember. Kind of makes sense. I mean, it wouldn't be hard to even think of if you're doing inverse trig functions. But what is cosine y? Cosine y, what's the cosine of angle y? Adjacent over hypotenuse. But I strongly suggest that you memorize it. Okay, so I'm going to write them all down for you. Okay? They're in your book. I had great notes to self.
The derivative of the inverse of sine.
So to clarify what I just did, super fast in AP Cal BC, is if you have y is equal to inverse sine of u, because I don't want to just do x. It might have like a composite function. All right, so the derivative is 1 over the square root of 1 minus u squared du. The book writes it like this, but much like logarithms and stuff, I like for you to have that feel of 1 over d, but it's the same thing as du over. Chain rule. All right, good news. If you have arc cosine, inverse cosine, it's interchangeable. I think Mr. Hill and I both use those words, I hope. The derivative is just the negative of it, which I could prove to you, and I'm not going to. Do you remember what all the c's are in our derivatives and integrals of trig functions? The c's were negatives, weren't they? Do y'all remember that? What's the derivative of cosine? Negative sine. What's the derivative of cosecant? Is negative cosecant cotangent. What's the derivative of cotangent? Is negative cosecant squared. The integrals of all those trig functions, I know you don't know very well, but same thing happens there. All right, so then the other ones, if you have y equals inverse tangent or arctangent u, its derivative is 1 over 1 plus u squared du, comes from that little triangle. Guess what arccotangent is? Negative 1 over 1 plus u squared. So you only have to memorize 3. Sine, arc, cosine is its negative. Tangent, arc, cotangent is negative. And what would you say about secant and cosecants, derivatives and integrals? Granted, I don't think you know the integrals very well yet. My fault. The antiderivative of secant is ln secant plus tangent. The derivative of secant is secant tangent. Aren't those always the longer ones? Sorry, this is how I memorize them. Arc secant's longer. So if I have y equals arc secant u, the derivative is 1 over u times the square root of u squared minus 1 du. And this is an absolute value because it's really been factored out of the square root. That's where that came from. Don't have time to show it to you. Guess what arc cosecant is? Same thing, but it's negative. All right, now aren't these enough alike to drive you crazy? Yes? Okay, you'll have a few of these for homework too out of the book. Just try to plug it right in the formula. Okay, so you're just trying to put it right in the formula. The way I remember them is arc sine. I just remember this one. Arc tangent's the easy one where everything's like no square roots and it's plus. Arc secant, do y'all see how it's the longer one? But it's a whole lot like arc sine. I think sitting in your chair right now, you would know that your dilemma would be where to put the u squared. Is it in the back or the front when you're memorizing these? The way that I memorized it when I was in college is that if I was doing arc secant, as soon as I wrote u down, I knew the next thing I was going to write was going to be a u. I knew those were stuck together right there. Okay, a u squared minus 1. That way I could remember sine was 1 minus u squared because it wasn't in the front. You can find your own way through that. Okay, so if I do an example real quickly and then we'll leave on time. So if I have y is equal to arc secant of 3x, I really need to give another example, but anyway, let me move on. I'll say 1 over the absolute value of u times the square root of u squared minus 1, and the derivative of u is 3. So my answer is 1 over absolute value of x squared root of 9 minus x squared minus 1. Because I can definitely cancel out 3 with the absolute value of 3, which is just 3. I think a lot of your work on these problems is simplifying them once some interesting things happen. They collapse in interesting ways, which we'll talk about later. But anyway, I'll post your homework. You'll be doing inverse trig. Please bring your you'll be doing Euler's and inverse trig. Hopefully none of them will be too time consuming. Capital REALLY will be your homework. And bring your 2003 packet with you every day until I sit over the problems, okay?
Yeah.